All right, we are live. So I'll just say a quick note to everyone on the live stream before we get started that you're going to be hearing my voice and seeing my presentation for this first 45 minutes. And then after that, we will switch to including the voices of the jury members who are connected through a separate Zoom account to hear the question and answers. Then we will go private for a period of time while they deliberate. And then at the very end, we will come back in and the president will announce the final decision. So let's get started. As you can see on the presentation, we're going to be talking about prediction and control of rolling noise in buildings. This is a project that I've been working on for the past 3 years with Madely's Research Lab, with INSA Lyon, and with Acoustics, which is a European Union Ph.D. program that my thesis is a part of. So we're going to be focusing on indoor structure-borne noise, that is, noise which transfers through the structure of multi-level buildings. And when we talk about this, typically the most common source that we talk about is impact noise, footfall noise from people walking, or the impact of falling objects. But the question which spurred this thesis was, what happens when the source is rolling? This could be delivery trolleys, shopping carts, office chairs, etc. Now, impact noise, regulated with the tapping machine, has a very standardized process, and we know very well what this sound signature looks like. So here what you're looking at is the spectral content of a tapping machine in red and a typical rolling noise spectra indoors in blue, as well as the attenuation of a classical floating floor in black. And we see that obviously tapping noise and rolling noise are very different in the time domain. One is a discrete series of impacts, whereas the other is a continuous low rumble. But also in the frequency domain, the frequency of impact noise is more broadband in nature because we are dealing with impacts, whereas the frequency of rolling noise is mostly concentrated in the low frequency domain. Most of that acoustic energy is centered around 100 hertz and can even have a maximum at 100 hertz. And this is important because when we look at the attenuation of classical floating floors, we often have a resonance around 100 hertz. So even though the total amount of acoustic energy might be lower for rolling noise than for impact noise, we can still have an increase in the overall structure-borne noise generated because of that peak at around 100 hertz. Now, my objective for this thesis, with all of this in mind, was twofold. It was to develop a numerical model which can accurately represent the physical phenomena present in indoor rolling contact, and which can estimate the relative benefit provided by a floor covering at reducing indoor rolling noise. That is, if we have a situation where we have a trolley rolling in the floor above, we can measure the structure-borne noise transferred through that multi-layer floor into the room below. And we can see what is the benefit of adding a type of floor covering on top of that floor and see what that does to reducing that rolling noise. The idea being that if we have this model, we can input different flooring materials and see which ones are better or worse at reducing this type of noise. So before we can move backward, we must first move, or before we can move forward, we must first move backward. So as it turns out, there is a lot of research which has already been done in outdoor rolling noise, in trains and in vehicles in particular. There's lots of pioneering works which were done by Remington in the early 60s to look at the train contact for rolling noise, by Thomson and Harris for expanding that to even greater domains for vehicle contact as well, even bearing noise as well. And then we also have works like Cocker, which expanded and tried to cover a very wide range of outdoor rolling contact. And for all of these, including indoor rolling noise, the main source of excitation is the small-scale roughness which exists between the wheel and the floor. So this small-scale roughness generates vibrations in the wheel and the floor and causes that sound to radiate. Now, we can't, unfortunately, simply use one of these existing outdoor rolling noise models for indoor rolling noise because there are several key differences between the different domains. First of all, the wheels and floors in indoor rolling contact can come in a great number of material constructions. You can have dozens or even hundreds of different materials that are used for trolleys and for indoor floors, whereas trains, we usually deal with one material, metal wheel and metal rail, and for tires, we usually deal with two materials, our rubber tire and our asphalt floor. So our indoor rolling noise model needs to be much more expansive in scope. We also have a much smaller geometry involved due to the small wheels and small loads, so we need a higher spatial resolution for those small scale roughness profiles which we need to measure, because it is this which is the excitation causing that wheel floor vibration. Discrete irregularities may be regularly encountered in indoor rolling noise. These are things like wheel flats and floor joints, whereas we typically only deal with one individual impact for other sources of outdoor rolling noise. Floor radiation is the primary noise generator in indoor rolling noise, and its transfer path is vertical and structure-borne. We're looking at the noise which transfers through the structure vertically from the floor above down to the floor below, whereas for train and vehicle contact, often we concern ourselves with horizontally radiating airborne noise, as that noise radiates outward from the passing vehicle. We can have structure-borne noise in outdoor contact, typically when we deal with trams, which are moving through cities. But again, that is not the same type of downward through the floor radiation that we deal with for indoor rolling noise. Now, in the existing models, there's many different ways of calculating the force between the wheel and the floor. You can use a single spring, assuming a point contact. And if you know the stiffness in that spring, you can then calculate the force, which is your contact force. You can expand to a line of springs or even a bed of springs to get 2 or 3 dimensions. Again, calculating the deflection of these springs to get your contact force. Or you can do a more comprehensive method like the Boussinesq procedure, where you treat your 2 surfaces as elastic half spaces, and you consider the interdependent deformation of these to get your contact force. In all of these types of modeling, we're using that small scale roughness as what is causing the deflection of these springs or of these elastic half spaces. And as I said before, this has been done, methods and devices that have been developed for measuring these small scale roughness profiles. And this works for outdoor rolling noise because for tire contact, we often have an area of contact between the tire and the ground, which is around 100 millimeters in length. For trains, it's around 10 millimeters in length. But for indoor rolling noise, it's usually around 1 millimeter, maybe 2 millimeters in length if we have a really high load and a really soft wheel. So for all of these, if you have, like we see in previous works, a 2D measured roughness profile with a 0.5 millimeter spatial resolution or a 1 millimeter spatial resolution for corrugated train wheels, or even in tire contact when we sometimes only concern ourselves with the tread pattern and not the small scale roughness, these types of methods won't work. We need a much more high spatial resolution when we're measuring these roughness profiles for indoor rolling noise to get that as an input. Now, I have actually taken some time to measure what the real area of contact is between trolley wheels and floors, and I did confirm that it is around 1 or 2 millimeters in contact. So it's, if anyone is curious, we do have that, that real world measurement which has been done. In addition to that small scale roughness, we also have discrete irregularities. Like I said before, wheel flats and floor joints, which can also generate noise. Now, methods have been developed in the past for calculating the geometric profile of these irregularities. But again, the focus is usually on the impact force from a single wheel flat on the rail, or if we do go out to the audio domain, what is the impact sound pressure level due to a single impact? It is very rare that these are considered to be regularly occurring, but it is necessary in indoor rolling noise. If you have a tile floor where you have floor joints every 30 centimeters, this existence of a regularly occurring floor joint needs to be accounted for in your model, because this is not only going to affect the impact force, but also the frequency of impacts will play an influence in that radiated sound level. So being able to regularly account for these is necessary in an indoor rolling noise model. Once you have the force of contact between the wheel and the floor, you then want to find out what is the response of the wheel. How does the wheel move vertically due to that force? This is often done using a spring mass damper system to model your suspension, which is relatively straightforward for trains and vehicles because we have suspension. We know what the stiffness and the damping factor is. But indoor rolling trolleys and other indoor rolling devices don't have a suspension. It is a wheel turning about a rigid axle. So you might think, okay, let's use a rigid mass in our system, but that won't work if we have softer wheels where there really is macro level deformation. So for an indoor model, what we need for this spring stiffness is the elastic stiffness of the wheel itself. And my question, which I needed to answer, was how do I calculate this stiffness? Moving on, once you have the contact force and the wheel response, you then need to find out how does this force and this movement translate into sound propagation. And for there, we can look at the propagation in buildings from other sources which have been researched in the past. We have, like I said before, mechanical excitation with impact noise and tapping machines. We also have other sources of impact noise, like rainfall noise, which is more of a randomly distributed series of impacts. For measuring the sound power of mechanical sources, we have the reception plate method, which is great for static sources, like if you have a washing machine or a jacuzzi. However, unfortunately, this doesn't really work too well for a rolling source because the radiated sound power of a rolling source depends on the wheel and the floor. So if you change the floor, you change the sound power of the source itself. So what this means for an indoor model is we need a method which can rapidly calculate the radiated sound power of the wheel floor system every time the model is run. And to do this, we can look at using a method such as the transfer matrix method, which takes our complex real-world system, our multi-layer floor, and splits it into a series of homogeneous layers for calculating the energy transfer from one side to the other. Now, this has been done in the past for both airborne excitation and structure-borne mechanical excitation using the finite transfer matrix method. And it's a great source to use in our model because we have a good balance of computational efficiency and accuracy. We could use other systems like statistical energy analysis, which are very computationally efficient, but not really that accurate if you have a complex system. We can also use finite element modeling, which is extremely accurate, but is quite computationally taxing. And because we need to be able to calculate this energy transfer every single time the model is run, it needs to have a good balance of the two. And that is something that the transfer matrix method can provide. So, with all of this being said, let's look at the methodology that I used for my indoor rolling noise model, which I developed. Here's an outline of the model. We have on the far side, we start with our input parameters, the wheel and floor material properties, the trolley properties, the speed of the trolley, the load on the trolley, the geometry of the wheel and the floor in contact, and then those small-scale roughness profiles. These are all used as input, and they are used in our contact model to calculate our contact force between the wheel and the floor. And based on this contact force, we can use this in our dynamic model to find what the wheel response is to that force. This is run in the time domain. So this is done at every discretized moment in time, and at the end we have a contact force and wheel response history for the whole rolling event. This is then converted to the frequency domain and used as input with our floor impedance to generate our sound pressure level radiated through the structure into the floor below. Now, for this contact model towards the beginning of our time-based model, we have what you're seeing here, which is an interpenetration profile of the wheel and the floor. We have the curvature of the wheel. We have that relative roughness profile between the wheel and the floor. We have our floor profile. And between these, we place our series of independent springs. Now, if you know the deflection of a spring and its stiffness, you can calculate its force. And this is done for the bed of springs in our model. A classical way of doing this is to predefine your contact stiffness based on the material properties.
Can you just check your microphone?
Yeah?
Yeah.
What do you mean, check it?
Is it on Zoom?
Mm-hmm.
It seems there's some difficulty to hear you.
Really?
But on the live stream, we have no difficulty at all.
Okay.
So just check for the Zoom.
Okay. I've been informed that apparently the Zoom meeting can't hear me very well. Unfortunately, there's not really much that I can do because I don't have a volume control for this microphone. I can try speaking louder, or I can try switching to a different microphone, but that might take some time to do so. But I'm not muted. Audio settings. It's all the way up. I don't know. Well, I guess we'll just keep going, and I'll try and speak a little bit louder. Oh, Fabian's coming back. Let's see what he says.
Comme un gros buzz. Maybe a fan or
There's a buzzing noise?
yes.
Okay.
But
Well,
just for the Zoom meeting.
just for the Zoom meeting.
It's not the same microphone.
No, it's not. Well, I can switch to a different microphone. How about that? Okay. This will not be wireless, so we'll have even more wires hanging off my face, but I guess we'll just have to deal with that. So, if we switch speakers, headphone. Okay. I believe we might have better audio on the Zoom meeting right now. Is anyone able to confirm for me that that is the case? No? Fabian is shaking his head. The same buzz. Is it is or is not better? No. That might be the fan of my laptop, which is quite far away, but unfortunately, there's not really much I can do about it. What? Is it better now? No. With the other microphone, it was better? Okay, well, we'll switch back to the other one. Sorry for this technical difficulty. We did our best to get everything working, but apparently there's not much we can do. The last thing I can try is switch to this. We have 3 microphones available. Let's switch to this one, which I don't think was giving us buzz last time, but we'll find out. This guy. One moment. That is also an option. How about now? Can y'all hear me any better now? Hey, there we go. Sweet. Yes. Sorry, what was that? Yes, I can do that. Yep, that's the other direction. Is that good? Okay, so yes, as I was saying, unfortunately we encountered technical difficulties, we can look at the work which has been done in sound propagation in buildings to see how do we want to develop our sound propagation model. Mechanical excitation, which has been researched heavily in buildings for impact noise with a tapping machine, and also rainfall noise, which is more of a randomly dispersed impact, has been looked at for structure-borne noise. Also for mechanical sources like static sources, a washing machine or a jacuzzi, these have been measured using the reception plate method to identify their sound power of that source. Unfortunately, if the source is rolling, it's not quite as simple to use the reception plate method because with a rolling source, if you change the floor upon which the source is rolling, you change the excitation itself, because the excitation depends on the roughness profile of the wheel and the floor. So what we need is a method which calculates the radiated sound power of the wheel floor system for every single time that we run the model, where we might have a different scenario. For this, we can look at the transfer matrix method, which is a method which has been developed for reducing a complex real-world multi-layered system to a series of simple homogeneous layers through which the energy transfer can be calculated. This has been done for both airborne noise and for structure-borne noise using the expanded finite transfer matrix method. And this is a good balance of computational efficiency and accuracy, which is really good for the situation that we would like to use it for. We can go for something more computationally efficient, like statistical energy analysis, but unfortunately that is not quite as accurate in many scenarios, particularly when it's really complex. We can also go with something extremely accurate, like finite element modeling, but that takes a long time to calculate, and when we want to be able to run this every single time we run our model, it needs to be at least relatively computationally efficient. And the transfer matrix method strikes a good balance between the two. So let's look at my methodology. For those watching the live stream, I just realized that you're hearing this all the second time, but unfortunately you are less important than the jury members, so we're going to do it all again for them. So we start on the left of our rolling model outline with all of our influencing parameters, the wheel and floor material properties, the trolley material the trolley properties such as its speed or its load, the geometry between the wheel and the floor, and that small scale roughness profile of the wheel and the floor. These are used as input into our time domain model, so at every discretized moment in time, we calculate in our model the force between the wheel and the floor. That is input into our dynamic model, where we use the wheel response to find how it moves vertically in response to that contact force. And at the end of our time domain model, we have for our entire rolling event our force and our wheel response. And this is put into our propagation model, which acts in the frequency domain in conjunction with our floor impedance to find what is the radiated sound power through that multi-layered floor into the room below which the trolley is rolling. So we'll start on the left with our contact model. Here we have an interpenetration profile which considers all of the geometry involved between the wheel and the floor. We have the curvature of our wheel, we have the relative roughness profile between the wheel and the floor, and then we have our floor profile. And between these we place our series of independent locally reacting contact springs. For these springs, if we know their stiffness and their deflection, we can calculate the force in them. And classically, this is done by predefining the contact stiffness as a function of the material properties of the wheel and the floor. And then if you integrate over the entire spring system, you get your force. I did not want to have to predefine my contact stiffness, so I chose instead to calculate the contact stress profile directly. And that, when integrated, will also yield the contact force. Now, to do so, I took Hertzian contact equations, which have been developed for surfaces of revolution in contact with one another. And I redefined these equations, or I rederived these equations as a function of my interpenetration profile, which means that I'm now including surface roughness and discrete irregularities in these Hertzian equations. What's important to note here is that when I remove this roughness and set it back to 0, we retain exactly our Hertzian formulation. And this is how we know and can be confident that these contact force equations are still based on Hertzian mechanics. Now for the inclusion of discrete irregularities, which can't be placed directly into the roughness profile, they need to be placed separately into the curvature profile of the wheel or the floor profile. We do this for both ideal and rounded flats. So a perfectly ideal flat, which is just a circular segment, or one which has had the edges rounded down over time. And this needs two main modifications before we can correctly add them into the model. First, I said before that we have a series of independently locally reacting springs, and to get these spring deflections to agree with Hertzian mechanics, we can't let them deform linearly. We have to make them non-linear by setting a square root over them. What this means is that we need to reduce the size of the radius of the wheel that is being used in this model, or else we're going to get an incorrectly calculated size of contact area due to those nonlinear springs. If we're reducing the size of the wheel, we also need to reduce the size of the flat spot by an equal amount. Otherwise, you're mapping a erroneously large flat spot onto an abnormally small wheel. So this is done for our wheel flats. And then secondly, we need to reduce the spacing of these flat spots around the wheel. If we don't, then we're going to have our model believe that we have an incorrect frequency of impacts as the wheel rolls across the floor, and that is going to change the radiated sound power. So we need to make sure that this angular spacing of the wheel flats is also reduced by a similar amount. For floor joints, a process is similar. We have our ideal floor joint, which is a step down in our otherwise zero floor profile. So if we know the total rolling length, the length of a single tile, and the length of a single joint, we can add these together to get our full floor profile, including floor joints. Similarly to how we had to reduce the size of the flat spot to account for that reduced wheel radius for wheel flats, we have to do a similar thing with floor joints, where we need to reduce the length of the floor joint. Otherwise, our model is going to believe that we have an erroneously long floor joint being contacted with that reduced wheel radius. So these modifications are what allow us to regularly account for these discrete irregularities in our rolling noise model. So we've got our influencing parameters. We have put them into our contact model and gotten our contact force. Now we have to deal with our dynamic model. Now, as I said before, we're modeling our system as a spring mass damper system, and our spring stiffness here, because there is no suspension, is the elastic stiffness of the wheel itself. Now, to calculate this, I ran a parametric study using a series of finite element models. So I took a cylindrical wheel, placed it in vertical compression along the axle, and calculated what the resulting stiffness was of that finite element model. And this was done for a series of changing wheel geometric and material parameters. So I ran a whole bunch of finite element models changing the wheel radius, the axle radius, the size of the contact area on the bottom, and also its Young's modulus and Poisson's ratio. And using this, I could find trends in the data, see how the contact, or see how the wheel stiffness changes with each of these varying parameters. And doing so identified a linear relationship for a couple items, the width of the wheel and its Young's modulus. So that is straightforward to take care of. We can normalize our stiffness by these two parameters to get a normalized wheel stiffness. However, there were two other parameters which had a unique relationship between this parameter and the wheel stiffness. And these were the size of the contact area and the axle wheel radii ratio, or the ratio between the wheel radius and the axle radius. So because we have these unique relationships, sort of logarithmic for the contact area and sort of S-shaped for the axle wheel radii ratio, we can develop a abacus, a lookup table which is dependent on each parameter, which links these geometric parameters with our wheel stiffness. I developed three different methods to do this. First was simply evaluating the lookup table using 2D interpolation. So if you know your contact area and your wheel axle radii ratio, you can calculate your wheel stiffness. An alternative to that would be to evaluate a series of one-dimensional polynomials if you don't want to use the lookup table. So you fit a polynomial to the data in one direction, and then fit a second polynomial to the data in that second direction. And that second polynomial can be evaluated according to the geometry to find your wheel stiffness. And then finally, a third option, if you don't want to use those first two, would be to use a single two-dimensional polynomial which is fit to the entire data set. So this is one polynomial which can be evaluated once for both of our unique geometry to find what is the resulting wheel stiffness for that particular wheel. So for each of these, this could be used as a state variable. That is, we have our set geometry. We can calculate what our wheel stiffness is and then use it in our time domain model. But the contact area depends on what roughness profile is in contact between the wheel and the floor at each moment in time, which implies that the contact area changes in size at each moment in time. So my thought was, well, does this mean that we can get a highly accurate wheel stiffness if we recalculate that wheel stiffness at every moment in time according to that new roughness? Yes, you can do that. As it turns out, while the contact area does change, it doesn't change enough to result in a significant difference in that wheel stiffness. So here what you're looking at is, for an entire rolling event, that stiffness being recalculated at every moment in time with the 3 different methods. And you see there's really not much difference in them, even when we zoom in really, really close. Which means that we can simply pre-calculate that stiffness using the Hertzian contact area at the beginning and then not have to recalculate it at every moment in time. Now, one more note I would like to point out before we move on to the next section. Here we're looking at those 2 parameters which had a unique relationship. And you see that we have our different data points from those finite element models which were run, which would be variations in the horizontal direction of these graphs. But we also have variations in the vertical direction. And what these different points are, they're actually variations in Poisson's ratio, because for each model I ran different Poisson's ratio of the material from 0 up to 0.495. Now, for areas of constant cross-section, we know that the effective stiffness depends highly on Poisson's ratio. As you increase it close to 0.5, it changes greatly. But for our cylindrical wheel in vertical compression, there is almost no change when you change Poisson's ratio in the resulting stiffness, which was an interesting discovery. What it seems to be occurring, what we believe to be occurring, is that the material is moving downward and outward into those horn-shaped areas between the wheel and the floor when in vertical compression. And it is this deformation which overcomes any effect that the Poisson ratio and the Poisson effect might have in the lateral directions. And this has implications beyond just acoustics, because there may be other materials of non-constant cross-section which might exhibit unique relationships like this between its stiffness and its Poisson's ratio. So we can use this calculated stiffness in our model to calculate our dynamic system, find that wheel floor movement at all moments in time. And now the last step is our propagation model. So we have our blocked force, which is our contact force from our contact model. We also have a system which links the normalized force, a multi-layer floor, and our radiated sand power. And these can be calculated independently of that blocked force, hence why I'm calling them normalized. They're only a function of the multi-layer floor itself. Now, what we want to do is link them. And this is done using the flexural force, which is going to be the contact force, including the response of that moving floor. So this, coupled with the impedance of the floor and the impedance of the wheel, will give us, in our multi-layer floor system, our radiated sand power. The wheel impedance is straightforward to calculate for us. It is our vertical velocity of our wheel under the blocked force. The floor impedance, this we're going to calculate using the transfer matrix method. So here we take a wave-based approach, and we're going to assume that the floor is infinite in the x and y directions, and that it's separated by air on both sides to semi-infinite fluids. If we have a point load excitation and a harmonic load and response, then we can treat and we can represent our system by an infinite series of plane waves, and this is used in our transfer matrix method, an example of what you're seeing here. Basically what this is doing is we have, as the name implies, a transfer matrix, which is a function of the material properties of each layer, as well as how waves propagate through those layers. And this is used to calculate the pressure and velocity on the input side and the pressure and velocity on the output side. This can then be combined layer by layer to find the global transfer matrix method, to find what is the energy on one side due to the energy on the other side. Now, as I said before, because we're assuming that we're infinite in our x and y directions, we need to use spatial windowing to reduce this. So basically, we're going to allow our infinitely large plate to propagate, and then we're going to send these waves through a window of finite dimension, and the resulting ones are what we're going to use in our model. And this method of spatial windowing accounts for any errors we might otherwise see in the low frequency domain in particular. Now, as I said before, these are not functions yet of the contact between the wheel and the floor. So we have a normalized floor impedance and a normalized radiated sound power. So this is using a normalized force of 1 Newton as the input into the floor. And similarly for the radiated sound power, we have a hemisphere of unit surface area over which we calculate our sound power. Because we have a unit hemisphere, this is essentially equal to sound intensity. And so the final step from converting from sound power to normalized sound pressure level is to include both the effect of our radiated sound power through the floor and the correction for the room absorption in the reception room. So this allows us to finally achieve the normalized sound pressure level in the reception room due to a trolley rolling in the emission room above. And because we're using this normalized sound pressure level, it allows us to directly compare, if we so choose, with tapping noise, because tapping noise is often calculated in a similar manner. So let's look at what some of the results of this model, what are some of the numbers that it gives us. The first thing we can do is look and make sure that it is accurately representing the physical phenomena of that wheel floor contact. So we have on our top graph our contact force throughout the rolling event in the time domain. In the middle graph, we're going to have the vertical wheel position throughout the rolling event. And then in the bottom, we're going to have our contact stress profile. And we can do this for a smooth wheel rolling on concrete. And here we see exactly what we would expect, where that small scale surface roughness is resulting in a modulating contact force and a modulating wheel position. If we put a rounded flat in between these and allow it to contact once so we can focus on a simple impact, we get exactly what we would expect. There's a impact force, a spike in our contact force profile at the moment of impact. There is a drop in the center of the wheel as that flat spot rolls through the area of contact. And then in the contact stress profile, we see that as the flat spot rolls through the area of contact, the position of the contact area relative to the wheel center shifts backward and then forward as that wheel flat rolls through that area, which is exactly what we would expect to see. Similarly, for an ideal flat, which has more jagged edges on its profile, we have a higher impact force. The wheel vertical position, of course, remains unchanged because it's still dropping by the same amount. And again, we have a more jagged contact stress profile as, again, that area of contact shifts backward and forward as we move through that wheel flat. For a floor joint, interestingly enough, we still get our spike in contact force, we still get our drop in wheel center, when we still see that shift in our contact stress. But here, our model is predicting that our point of maximum contact force actually happens ever so slightly after the position where the wheel is at its lowest point, or where the wheel center is at its lowest point, because the point of maximum contact actually happens on the far side of the floor joint, not in the center, because the wheel is going to contact the far side of the floor joint before it bottoms out on the bottom of the floor joint. So all of these things, all of these graphs are showing us that our model is indeed accurately representing the physical interaction between the wheel and the floor, both for our surface roughness and for the presence of discrete irregularities. If we want to compare what the differences between model and experimental sound pressure levels, then we first need to get some experimental data. And to do this, I used 2 different trolleys to measure the radiated sound power in some test locations. We did one at an industrial partner in France, and we did one at an industrial partner at Level Acoustics and Vibration in the Netherlands. And for both of these, just as the model expects to happen, we roll the trolley in the room above and we measure the sound level in the room below. And this was done both for bare concrete and for 2 different floor coverings, rough PVC and smooth PVC, for both smooth wheels and wheels with a series of non-periodic flat spots around the perimeter. So what I'm going to show you here, I'm going to explain a little bit before I show it because it's kind of confusing. Anytime you see a solid line, these are model results. Anytime you see a dashed line, these are experimental results. Here we're comparing the influence of changing the wheel and changing the floor. So your blue line is going to be your concrete, your orange line is going to be rough PVC, and your yellow line is going to be smooth PVC. For smooth wheel, a wheel with ideal flat spots and a wheel with rounded flat spots. So here if we look at the normalized sound pressure level with these different situations, we see that there's relatively good agreement between model and experimental results. We have a tendency here to underestimate a little bit for the smooth wheel and the rounded flat wheel, but the ideal flat wheel is spot on. An alternative is to see what is the relative benefit of adding one of these floor coverings. So we take the sound level from the rough PVC and subtract it from the sound level of concrete and do the same for smooth PVC. And here we get kind of a delta normalized sound pressure level. See what is the relative benefit of adding one of these floor coverings. And again, we see, particularly for the flat wheels, that we have quite good agreement between model and experimental results. The deviation in high frequency for the smooth wheel is mainly due to the fact that in this high frequency range, when you have no discrete irregularities, there tends to have a lower signal to noise ratio in the experimental data, and so it becomes harder to estimate what the resulting sound pressure level is in that high frequency range where there's not a lot of acoustic energy. An alternative to visualizing this data is we can look at how do the results change when we change one of the influencing parameters, such as the load on the trolley. So here we have our blue line is going to be our trolley rolling with a 10 kilogram load. Our orange line will have a 20 kilogram load, and our yellow line will have a 30 kilogram load for both smooth wheel, ideal wheel, and rounded flat wheel. And interestingly enough, the load, when you change the load, either double it or triple it, the radiated sound power level doesn't really change that much. You might think that intuitively, okay, if the trolley is heavier, it's going to be louder, but here the difference is very slight. And so it's promising to see that that small difference in experimental results is also present in model results. So our model is accurately representing that little influence of the load on the radiated sound power level. And then we can also look at the influence of trolley speed. When you go blue, a slow speed, orange, a medium speed, and yellow, a high speed, what is the difference in the radiated sound pressure level? Conversely to the added load, we know that there is a very high influence of the speed on the radiated sound level. When you make the trolley move faster, it gets much, much louder. And we see this large dependency on speed in both experimental and model results, which again is very promising to see our model is accurately capturing the influence of speed, both for our normalized sound pressure level and for our relative benefit. Again, we see in the smooth wheel that as we get into that high frequency range, that signal to noise ratio kind of makes it more difficult for us to accurately calculate those results. However, fortunately, it is this high frequency range where because we have less energy, it's less of a focus. That mid and low frequency range is really what we're focused on. Now, in building acoustics, oftentimes when we're communicating with non-professionals, we will reduce our complicated frequency spectra into a single number rating, or what are sometimes called global indicators. And we can do the same thing for rolling noise to see if the methods for calculating these global indicators for impact noise in particular are effective or result in a correct representation of the data for rolling noise. So here we can look at, for a smooth and flat wheel rolling on concrete, what the difference is between model results in blue and experimental results in orange for our signal number rating, our normalized weighted sound pressure level. And then similarly with rough PVC and smooth PVC. And here we see that between model and experimental results, there's quite good agreement. So our model is doing a good job at calculating that single number rating with respect to that experimental data. So that's good to see that our model can also capture that single number rating as well. If we want to, again, see what the influence is of the added load on that single number rating, just as in the experimental results, we're seeing a very small influence of the load in the model single number rating, which is promising as well. We also see that the trend line is if not perfectly accurate, very, very similar. We don't see when we increase the load that there's a significantly large difference in the trend line between the different loads for model and experimental results. And then for trolley speed, similarly, we can compare model and experimental single number ratings. And again, we see they're not obviously perfectly accurate, but we do still see a tendency to have a similar agreement in trend line between experimental and model results. So it's good to see that we do have good agreement between these different trends. They're not perfect, and the reason for that is that this single number rating, the normalized weighted sound pressure level, is still based on the reference curve for impact noise, because no reference curve for rolling noise exists, because nobody has researched this topic before. So that could be something which could be beneficial in the future, is to develop a reference curve for rolling noise to improve the accuracy of these single number ratings. So, in conclusion, the developed model estimates the normalized sound pressure level of an indoor rolling trolley and the relative benefit provided by adding a floor covering on top of that base floor. The developed model can accurately capture the physical phenomena present in indoor rolling noise, and it is specifically adapted for multi-level buildings and multi-layer floors, transferring that structure-borne noise vertically into the room below. The contact model accurately predicts the contact force between the wheel and the floor, and we have discrete irregularities which have been able to be regularly accounted for in our model. For calculating the stiffness in the dynamic model, we have developed polynomial relations which can be used to evaluate that wheel stiffness as a function of the wheel geometry. And in doing so, a unique relationship was identified between the wheel stiffness and the Poisson's ratio of that wheel material. The model has finally been validated with experimental results from 2 different laboratories, which is good to see that we have agreements between these 2 different labs in our rolling noise results. Moving forward, what can this model be used for? Well, as I said towards the beginning, the idea is we can use a model like this to input different flooring systems and identify which ones are better or worse at producing rolling noise. Because the type of excitation is so much different than impact noise, there's no guarantee that the techniques developed for impact noise will be effective at reducing rolling noise. So this is exactly the kind of model which can be used for that type of scenario. Additionally, in going through these experimental results, it was identified that it would be highly beneficial to have something like a standard rolling device to be able to conduct these rolling noise measurements. Just like we have the standard tapping machine, which no matter which lab you use in it, we can be relatively confident that you're getting results which can be compared more or less. It would be beneficial to have a similar kind of device, a standard rolling device, to be able to compare between labs conducting this indoor rolling noise research. And then finally, all of the focus on this thesis has been looking at vertical downward transfer of trolley rolling on the floor above, transfer downward to the floor below. But a beneficial work to do in the future would be to flip this around and expand to upward or lateral transfer paths. And this has been done for other sources of static mechanical excitation in concrete buildings, though not in lightweight buildings. So perhaps using these methods and adapting them for rolling noise could be a fruitful endeavor. As far as where this research has been, the polynomial relations that I discussed were published in a journal article in Acta Acoustica, and I have 2 other journal articles which are under review, one for the rolling noise model itself in JSV, and another for the standard device suggestion in Building Acoustics Journal. And then I have 2 conferences at which I presented in the past, and 2 more which will happen at Forum Acousticum this December. I used some copyrighted images which are under the Creative Commons license, so legally I have to show their references here for anyone that is interested. Thank you very much for your attention.
Just move to the questions. And so for that, I suggest to start by your 2 referees, Wolfgang Kropp and Denis Duhamel. And so, Mr. Kropp, you have the floor if you have any questions.
Yeah, I'm supposed to have questions, am I?
Of course.
Well, first of all, I would like to thank you for the very, very nice presentation, and of course also congratulate to the work.
Thank you.
I read your thesis, was quite interested, and it was a pleasure to look through that. So I really think it's a very nice bit of work.
Thank you.
The questions I have are often general nature. I will avoid to go very deep into details, but we can start with a very general question, which was always running in my head. And you touched it a little bit today when you, and of course you could have guessed this. Why have you chosen exactly this form of contact modeling? That's I mean,
Yes.
you have an extremely nice first part in your thesis on literature study, which really tries to track the whole thing on contact modeling, and it has so much details in it. And at the end, you decide on one model, and one way of modeling. And my question is just why? There's nothing wrong with it. I just want to know
No.
why.
So as I was doing that literature review and I saw all of these different methods that had been developed, originally the I personally have a tendency to overdo things, and so my first thought was this Boussinesq method sounds interesting because it takes into account that elastic deformation. So at the beginning, that's actually what I started looking into as a possible adaptation to be able to account for the elastic deformation of the forces. But as I read more into it, I saw more literature which is showing that, yes, while it is highly accurate, in many scenarios, it's actually not necessary because we can get very accurate or accurate enough results using an independent bed of springs. So that is actually what made me want to go to the bed of springs method, because I was also aware that this is the model which is going to need to be able to be run very quickly. And I wanted to make sure that we had a good balance of computational efficiency and accuracy. So in the end, yes, the bed of springs was chosen because I felt like it was a relatively robust method, a method what I could employ to three-dimensional contact without having too high of a calculation time.
But then you could also have chosen the way Thomson has chosen at the very beginning, and use just a spring formulation, one contact spring he has used. What was ruling out that, in your opinion?
The reason for that was one-dimensional contact and a single contact spring. I would need to implement myself an analytical contact filter, because the higher frequencies are going to be overestimated if we only have one-dimensional contact. And so my desire was, if we can implement a 2D or three-dimensional model, it will naturally account for that contact filter, and we won't have to pre-filter our roughness profiles in order to use a one-dimensional model.
And that's completely right, because then you would have the question, what is my contact filter? And that's you have a degree of freedom which is not so simple to decide on. And that depends on your geometry, and depends on your roughness, and it depends on the roughness of both wheels. And it's actually, in your case, but it's the same for Thomson, it's actually a 2D contact filter, both in width and length, which you have to take into account. When you work with this model you have chosen, you use this, we can call it Winkler bedding, or what you want, with isolated springs. The question I also used that at the beginning, and my question was always, what are the consequences that these springs are not connected with each other, so that they can act separately, which is not true in reality. We agree on that. So the question is, what is actually the consequence? Could you describe what in your point of view the consequences would be?
In my point of view, the consequence of that is you can overestimate the points which are in contact between the two surfaces. Because if you have an elastic model which takes care of that elastic deformation, if you have a really high asperity next to a really low asperity, well, that lower asperity is probably not actually going to get into contact because of that elastic deformation due to the high asperity. And so
the risk of using independent springs is you might get an overestimation or an over-influence
Mm. Mm.
of the surface roughness.
Okay. When you think about your model as you also use the Hertzian contact in some. Could you elaborate a little bit on this? I think I have understood why you did it, but you mentioned it also in your presentation. Maybe you could explain it once again to me, if I understood you right there.
Why I wanted my model to agree with Hertzian contact?
Yeah.
I wanted it to agree with Hertzian contact because, I mean, personally, it's a very robust field of research which has been highly worked on, and we have equations which were developed, which we know these equations accurately predict the true area of contact between the wheel and the floor. And so I wanted a system which could provide that to me when I removed that roughness profile.
Because one of my questions was always when I work with contact is area between two bodies which are in contact. Think about you have a very rough surface and you press down a rubber. Would you expect that the area is bigger or smaller than when you have a very dense surface which is smooth?
I would expect a larger surface because you have higher deformation.
So you will have a variation due to the roughness for your contact, will you?
Sorry, what was that? I didn't hear.
You will have an variation of the area of contact due to the roughness.
Yes, and you can see that. You know, if you take the model and set the roughness to 0 and plot your area of contact, it'll be X, and then if you add the roughness back, you might get a slightly different area of contact as the edges will move up or down.
Yeah, but also because your contact will be softer. If you have just a few points in reality, not talking about the Winkler model, but in reality, but even your Winkler model should show that if you have just a few points in contact, you have to go further down to get the same load.
That is very true. Yes.
Yeah. So this is actually the difficult part in contact model, which is also in trouble when you have a Winkler bedding, but also when you have a Hertzian contact, but also when you use others. We actually do not know the real area. And now I'm talking about the area of real contact. Is that something you're familiar with, this formulation of the area of real contact?
That was something that I was also intrigued by, for that same reason that there's no way to measure it directly, because if you do measure it, then you're changing the area of contact by placing something in between the two surfaces, which is able to measure them. And I tried to do as best as I could. I used some pieces of pressure sensitive paper placed in between the wheel and the floor, pressed them down, and they colored themselves depending on the area of contact. I knew that the presence of this paper would change it, and especially when you have a curved wheel, the paper kind of has a tendency to curl upward around the wheel. But I wanted to do a sanity check. I wanted to see, okay, at least are we in the general ballpark of what these calculations are telling us we should have? But I agreed that I had that conversation with several people. That is an interesting question. We can't calculate this directly and be absolutely certain that we're getting experiments.
It's very hard sometimes. But I think if you think about back now, you have done this model and you have it tested in to experimental part, which I like very much, this part in your thesis. And I'm aware that this is a very tough experiment, as you also described. It's not so simple. If you think on your experimental part, and I come back to the contact model, what do you think are the most difficult parts in your whole project? Is it the modeling, or is it, if you think, what is actually most difficult to get?
I feel that the most difficult part for me was the experimental aspect, because there are so many extraneous sources which can cause noise. You can have the trolley can rattle. You can have extra noise sources. You cannot be absolutely certain
Mm.
that the floor upon which you are rolling is going to be accurately represented by your model. So I guess in that sense, maybe the both, a link between making sure that the experimental data is accurately able to be compared to your model.
Yeah, I was thinking about that because when I look at what you actually try to do, I mean, a model, that's a quality of the model. That's one point you need, but you also need the quality of the input data for your model for being able to compare. I think we both agree that your model certainly represent a trolley. That it does. So rolling on the floor. It's a generic model for that. It shows the right trends when you test it, and it shows the right behavior for when you modify parameters. But the input data, you can't really be sure that you have captured the right input data for everything in that.
No, you
So when
can't
you
be
think
certain.
about what input data, yeah. So what input data do you think are most crucial in your for that test?
At
If
the
you had time now and redo it.
mhm. Interestingly enough, at the beginning, my hypothesis that was that the surface roughness profile would be very important. Um, and as we found out, it is important. You need to have it. If it's not there, then you're not going to get an accurate model. But the
Mm,
material parameters of the floor, the elasticity, the damping loss factor, those things had a much higher influence. And so it was really
mm,
these parameters that particularly for concretes, we have a very good understanding what its damping loss factor is. But for these PVC floor profiles, perhaps what I'm using in my model is not perfectly accurate, and it's leading to differences. And that is an area where it has a high influence, and we're still not super certain that it's experimentally accurate.
mm. I had a question in that context. When you say it's the stiffness of the PVC floor, did you try to correct your contact stiffness in some way to adapt to a softer ground?
In the contact model, we don't do any specific correction when you change the floor. We did go back and forth between the thought was okay if you have PVC that's going to be sitting on top of concrete. I started with calculating the effective Young's modulus of the concrete PVC system, but for contact that's not really accurate because it's only the top layer which matters in this case. So
Mm,
in the
mm.
end, I'm only using the elasticity of the top layer, not the lower layers. That does bring up a
Okay,
good question,
but
though.
I think that's
Go ahead.
mm, mm. No, but go ahead.
I
Yeah.
was going to say that does bring up a good question, which is, what if you have a hard top layer but a soft decoupling layer below that? Well, then I need to be able to account for the effect of that soft decoupling layer, but only in the bulk level deformation, in the macro movement of the wheel, not in the contact, where the small scale contact between the wheel and the floor is still only going or mostly going to be dependent on that hard top layer.
Mm. But that's right. So if you go back now, I mean I just a few words about your floor because your floor model you use the transfer matrix method, which is very nice. You that you could use a much more accurate method, and I'm always doubtful about very accurate methods. You talked about time element, but isn't it that in the same situation then you have to know all the parameters
Yeah,
in detail?
theoretically, if it could be done, it would be more accurate, but in reality, it wouldn't be helpful.
I think the transfer matrix method is a quite good approach in that. Uh, I might have missed it, but did you in some way validate your transfer matrix model of the floor?
No, we didn't do. I didn't do a finite element model to validate that.
No, I thought
Um,
more by a measurement, for instance,
oh,
with an impulse excitation or something, not with a rolling, but with something.
I do have data for the mobility of the concrete floor, which was measured at level acoustics and vibration, but not for the multi-layer system. So I don't have that
Mm,
including the PVC on top.
mm, 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 mm. Going back to now, after having all this done, would you design your model in the same way? What do you think could be improved in if you now can go to the different parts and say, okay, I could do that differently or that differently? What would you start with?
Hmm.
You had an outlook, but the outlook, of course, was more in the future, not going back to redo it.
Yeah, if I could do it differently, it's hard to say. I think. I mean, I spent a lot of time worrying about the influence of the roughness, and as it turns out, it was not that much of an influence, and also on the load. Maybe I mean what I would do differently was I would have started with a series of experimental tests right at the very beginning where I could identify parametrically these are the influencing parameters, know what each of them is and what degree it has, and that would probably have allowed me to be more focused in where I put my time and effort in the model development. For example, I
Mm,
probably would
mm,
put more of a, I would want to change the model so it has more of a, it captures more the elastic properties of that multi-layered floor. For example, getting the
yeah,
influence of
yeah,
a
that
of
was
a
thinking. Mm, mm. Because you at one point you talked about blocked force, and that's certainly a good approach. But the question is really if it's a blocked force at the end, if you go on a real floor, especially if you have multi-layer floor with some coverage, is that really blocked? So
true.
I'm not sure about that. Yeah, and
Yep.
often when you have these floors which you used, um, where they were not always built extraordinary as a lab, wasn't there? Was it lab floors or was it floors you have actually in a flat as well? How was that?
So the for the industrial partner in France, it was a lab grade 2 level reverberation chamber. So it was a 14 centimeter concrete slab,
Yeah,
which we then placed on top our basic. They look like giant puzzle pieces for the PVC.
yeah,
For level acoustics, it was slightly more complex. It was a transmission room. So we had a hole in the middle, which we put a 10 centimeter concrete slab inside, which was isolated on the corners with elastic supports, and then put the PVC puzzle pieces on top.
mm. But what I was striving at is that often coverage is often not a simple thing. You will always have a not perfect under beneath if the surfaces are not treated very special, and that could already change the dynamic properties of your partial dynamic properties of your layer. So I was
Sure.
more trying on that. I think I will make a stop here with and once again, thanks a lot for your effort and all the nice work. So I leave to the
Thank you.
next person.
All right.
Well, thank you.
So thank you, Wolfgang. We now move to the second referee. So Denis Duhamel, the floor is yours.
You are muted, unfortunately, so I cannot hear you.
Denis, are you here? I think that we have a technical problem.
Okay, is it okay now?
Yes,
Yeah,
I
yes.
can hear you now.
Okay,
So you can ask your question. The floor is yours.
okay, okay. Thank you, Mr. President. So I think this thesis is quite interesting because for many years we have seen a lot of work about railways noise or what are your noise, and this thesis is very among the very few new ideas in this field. So I think it's quite interesting. Perhaps it can even provide some idea about to deal with these old problems. So it's quite interesting for me. I will ask some question. First question is about the radiation. You say you are certainly true. You say that the floor is a main radiator. But can you say a little more? Can you compare the sound level radiated by a floor to a sound level radiated by the wheel? Because for road noise or railway noise, the wheel is the main radiator. So in your case, what can you say? Can you prove what you say, that the floor is much, the sound level radiated by the floor is much higher than sound radiated by the wheel?
So for that, I will say two things. The first is if you look at in the early stages how wheels, particularly train wheels, were first analytically considered for their radiation, a common approach was to model it as a disk radiating in the axial direction. So if we want to take that approach for our system, the acoustic amplitude of your radiating disk is going to increase the square of its radius. And so if you have I believe the calculations I did, if you have a 50 millimeter radius wheel and a 1.5 meter radius floor, which would still be a very small floor, then you're going to have something like a 900 times larger amplitude for the floor radiation than the wheel radiation. If you have four wheels, if you have a four-wheel to trolley and assume that they are incoherent sources, then you still have 450 times the amplitude. So my thought process was from a purely first shot analytical standpoint, the amplitude of a radiating floor, it's just able to generate so much more acoustic movement that it's going to overpower the acoustic radiation of the wheel. But from a second point, any radiation that the wheel does have, even at its small geometry compared to the size of the floor, it's happening airborne in the emission room. And so we're not concerning ourselves with it in this case because we're looking at structure borne down to the floor below. If we are concerned with the airborne radiation of the wheel in the emission room, there are already existing methods in building acoustics for taking care of that. So that was my personal argument for why I said I'm going to make the assumption that it's not a significant radiating factor.
Okay, thank you. The second question about the wheel. You have chosen to a model of the wheel which is mainly stiffness. You consider the wheel through its stiffness. I think it's quite correct for low frequency, but probably it's not true for higher frequency because you have some modes of the wheel which will appear. But do you have an idea of what is the frequency range over which the wheel can be modularized only for stiffness and nothing, not using a more complex model? Mm-hmm. What is the frequency range? Is it 1,000 hertz, 10,000 hertz, more? How does it compare?
I don't know an exact number because I didn't, in fact, do that calculation to find what that response was. I would say that my hypothesis, which I'm going with, is because in this indoor rolling noise, almost all of the acoustic energy happens below 5,000, most even below 1,000, that the high frequency range, if the stiffness of the wheel is only valid up to a few thousand hertz, it's not a large concern because once it becomes less valid, we're already in the zone where there's just not enough acoustic energy for it to result in a high error.
Okay. Now you have propose three methods to estimate the stiffness of the wheel with different abacus, and I remember that you compare these methods in terms of computing time, but what can you say about the accuracy of these three methods? Are they the same, or one method is more accurate than the two others? What can you say?
Because the three different methods all pull from the same data set, they're very, very similar. There's very little difference between what the results are going to be using each of the three methods. The desire behind why I was interested in developing these two different methods was from the calculation time standpoint, and also from a dissemination standpoint. It's easier to disseminate and to publish this is the polynomial versus having to disseminate the entire data set for the lookup table.
Okay.
But again, because it's all based on the same data, there's almost no difference.
Oh, okay, thank you. I have also seen that you have a very short study about the influence of speed on the sound level, noise level. I think it's quite important for road tire noise or railway noise, and this sort of thing is well studied for this problem. Have you been able to compare what you obtain dependency on your sound level in terms of speed of a trolley compared to what we have seen in, for instance, in road noise? Is it the same or is it different?
I didn't do a direct comparison. I can tell you that based on my knowledge of the literature and the focus which is placed on outdoor rolling noise, that yes, we know that for outdoor rolling noise, the sound level does increase linearly with the speed to a point. Then for trains, it usually sort of levels off. Also for impacts, once you have loss of contact with the impacts, you're going to have a level off in the impact noise. But I didn't, because for trolleys, you can have a difference in speed. But again, I mean, from my situation, I was comparing 0.5 meter per second minimum to 1.6 meters per second maximum.
Yes, the range is
not
quite
that
limited.
much of a difference. So we want the model to be able to account for it because we know there is a difference, but still it's a small range.
Okay. Yes. One thing also, because in your problem it's a complex problem because you have contact forces, you have a radiation, you have a transmission through a floor. Is it possible to do something in free field, as we do, for instance, for the road tire noise we study in free field? We have no transmission through the road. Is it possible to do an experiment in free field that will provide some interesting information for, without considering the transmission for floor? Just the radiation of the sound. Is it possible to do something?
That could definitely be done. I didn't do it because again I was focused. Well, in a sense I did do it because when I was running my measurements, I had microphones in the admission room and I was measuring on those as well, but I didn't analyze the data. But you could measure it the same way that impact noise is measured, where you have a series of randomly spaced microphones throughout the room. Another option could be to follow the approach which is used for measuring the pass-by noise of large machinery, where you have a hemisphere and you roll the device through the hemisphere, and that gets you what your pass-by noise is. But that was not something that I focused on now.
Okay. And last question. In case of, for instance, road tire noise, I know very well, you have what we call the air pumping. Of course, it's not the most important point in your case, but what you can say of air pumping in your case, is it there is absolutely no air pumping, or just a little, or we can ignore it?
In my case, I'm ignoring it. For air pumping to occur, you need to have, I mean, in tire noise, you have a very deformable elastic tire, which is going to, we know, change highly depending on that roughness contact. But for our wheels, we don't really have air pumping, one, because the wheels are solid, but also because they're just not deforming enough for it to be influential.
But sometimes you have cavities in the, for instance, in your floor, you have in one case, you have some cavities. So perhaps it's not impossible to have air pumping, perhaps, but your focus on low frequency probably is not very important, but in case of cavities in floor, there is a possibility of having some.
That's true. I mean, if you have, for the case of a floor joint, you could have air pumping as the wheel rolls across the floor, but that was not a focus of mine.
Okay, I agree that it is not so important, but it would be interesting to estimate because this is a very complex problem with many mechanical factors. So it's quite interesting to estimate when we ignore something, to be able to estimate what is the level we ignore, what is the level of noise level that we can so that we can ignore this phenomenon. I agree that it is very difficult because even in the case of road tire noise, it's the influence of the air pumping is not very clear, even after many years of study. So it's a difficult problem. But perhaps in your case, if we can ignore at all air pumping, it can have some give us some idea to deal with other road or railways noise generation.
That's a good point.
That's why this problem can be quite interesting, because if there is only structural noise, it can provide some good idea of how to deal with these problems. Mm-hmm. So thank you very much for your work, and congratulations for this quite interesting work.
Thank you.
So thank you, Denis. Madame Guigou, you can ask your question, please.
Okay, thank you, Mr. President. Well, first, I would like to say that the dissertation is well written, it's clear. I do believe the goals have been achieved. So thank you for this work.
Thank you.
I still have a lot of questions. And the first one is related to figure number 4 of your dissertation. And I think you did show it today. You know, it's at the beginning. It does show the comparison between the impact noise and the rolling noise.
Yeah. Yeah, I know which one you're talking about.
Okay. And in that figure, you can see that in the low frequency range, we have similar behavior between the two different type of excitation. And when I saw that, I was like, maybe in the rest of the dissertation, he would show the impact noise of the different system he tested, but I didn't find it. So I was quite disappointed, because for me, that might be a simplification. You know, instead of doing rolling noise, you can just measure the impact noise and kind of try to adapt something. So
to be fair, that was something that as I was running my experiments, I thought as well. I thought, oh, it would be really nice to be able to run an impact noise test here to be able to compare. But unfortunately, due to time constraints and other logistical reasons, I wasn't able to get around to it. But I agree. I mean, you can have a situation where maybe they are similar, but at the same time, they're only going to be similar in the, they're not going to be similar in the temporal domain. So you might still have differences there.
Yeah, and it's probably similar because the floor is relatively stiff in that case, I would say, or maybe. Okay. I have another question related to the dynamic model of the wheel. Then you introduce the stiffness and the damping in your model, and I was wondering why did you choose this type of damping, and what is the damping you applied in the different models you developed? Because I don't think I saw it mentioned.
So in my case, as is the case in some other train models, the damping is not really a physical parameter because, again, we don't have suspension, and the actual damping of the wheels is not going to be very significant. In my model, I use it to tune the model to make sure that we don't have it going chaotic or having ridiculous resonances. So this is a similar approach which is done in other rolling noise models where the model is developed, and I looked at different damping factors until I found the one that I saw was resulting in the most realistic, what I felt to be a realistic response. And for my model, it ended up being 0.4. So I use a damping factor of 0.4 for my model.
But you use a viscous damping or hysteretic damping?
Yes, it is viscous damping.
Okay. So that would be good maybe to mention it somewhere in the work, because I'm not sure I saw it. So, yeah. Another question related to that is figure 2.23 of the dissertation.
Mm-hmm.
When you look at the receptance of the wheel,
yes,
you can see that in the frequency range we're interested in, which is above 50 hertz, I would say only the mass is important when you look at the curve. And so I was wondering if it was the same thing for all the different parametric study that you did on the wheel or not.
I did not, to be fair, I did not look at the receptance curves for all of the different parametric studies that I ran. Mm-hmm. At various points throughout the process, I did switch to modeling as a rigid mass to see what the effect was, and it unfortunately we kind of had a similar problem with the damping, where if it is modeled as a rigid mass, you can have the model, because we're allowing for loss of contact, the model can go unstable. Once loss of contact occurs, it's just going to start bouncing wildly. So that's why I needed a elastic model, or a spring mass damper system in there somewhere.
Okay. So it's to control the instability of the system.
Correct.
Okay. Another question, and I was rather surprised by equation 281 in your dissertation, when you only use the real part of the mobility of the structure to evaluate your force. Can you elaborate on this?
Yeah, so this was, and I believe, as I said, it's kind of an interesting thing where at the start, the equation that I used was both real and imaginary. However, through just a trial and error experimentation, it was found that only using the real part resulted in a better agreement between experimental and model results. When the imaginary part was included, particularly in the mid and high frequency ranges, there was a tendency for it to underpredict even greater. The explanation for that isn't, I don't really have a perfect one. I'm not fully aware as to why, but for whatever reason, the best argument that I could come up with is it's possible that taking into account the imaginary part also accounts for the dissipation twice. But even then, it was more of, we observed that this works better, so we're going to use it, but it would still be beneficial to do more work into why it works better.
Do you think you would have to do the same thing if you just calculate impact noise, or it's just in that case you have to do this?
No,
is it because of the excitation, or I don't know? I was wondering.
I think it is for rolling noise excitation, because I'm not certain, but I don't believe that a similar phenomenon is observed with impact noise.
Okay. Because I don't use this expression. I use the real thing, so that's why I was rather surprised. What else? I think you already commented on the fact that you did measure the sound pressure level in the emission room, but I didn't see them anywhere in the dissertation. So I was surprised why you mentioned that you did the measurements, but then at the end we don't see anything. So I was wondering if you did compare.
It was used kind of just as a reason to be complete, because I made the decision to follow the standard for impact noise for measuring, and because that includes measuring in the emission room, my thought process was perhaps this can be used in the future for doing a comparison, but I didn't end up using it.
Okay, so maybe you could remove it from. I don't know. I mean,
that is true. Yeah.
Because then you ask yourself question when you read the document. I was wondering if it would have been a good idea to measure the displacement of the wheel while you're doing the measurements to get closer to the force you're injecting into the floor. Because if you look at the trains, now we also do a lot of measurements on the axle box, really close to, almost on the wheel, on the axle. And so I was wondering if that would have been a way of validating your model rather than looking at the end of the chain, which is the sound pressure level, maybe something in between. What do you think?
I agree. And as a matter of fact, for my first round of measurements, I did measure, I had an accelerometer on the trolley frame, not the axle. Looking at the data after the measurements, I found, because my model was not yet set up to measure the acceleration of the frame, I didn't go further than that. It was really just used as a sanity check to make sure that we were getting relatively similar movement. But again, like you said, it's not present in the dissertation because I didn't go further with that.
Okay, but you agree that it could have been a way of validating your model a little bit. Okay. Okay. All right. Another thing that kind of bothered me, I mean, not in a really bad way, but, as being a building acoustics acoustician, is your comment that you have on the adaptation term related to impact noise. Okay.
Okay.
I mean, for me, looking at just the value of the adaptation curve doesn't mean anything. And I agree with you. You only have to look at the adaptation term when you add it to the LNW, okay? And when you do that, you get rid of the reference curve. And that's why we have this adaptation term, okay? So you don't, for me, it would have been much more interesting to compare measurements and prediction in terms of LNW plus CI,
okay,
rather than LNW. And then I have another comment related to this, that we have a special adaptation terms that start at 50 Hertz. Like you're doing your measurement starting at 50 Hertz. I think it would be a very good idea to look at this index as well. Okay. And that allows you to not to think about the reference curve. Okay. It's like an average level that you obtain with the pressure level. Okay. So I think I would like that to be modified in your dissertation.
Okay.
Something that wasn't clear to me when I read the document was like all the floor coverings that you tested in the different laboratories and those that you measure the roughness are all the same.
Are you referring to the PVC floor covering?
Yes. Mm-hmm.
Yes, for those, I had measured the rough PVC and the smooth PVC.
Okay, and so these are the same samples that you take to the different laboratories?
Yes. Oh, yes, yes. I brought with me the different floor coverings, and so they're the same between labs.
Okay. I think that's pretty much all that I had in mind for question. Yes, so next person.
Thank you.
So thank you, Catherine. Before to give the floor to the two supervisors, I would like to ask my questions. So first, I would like to say, Mr. Edward, that I really appreciated the reading your manuscript because it is very well written and clear, and so that's a good point. And also, I would like to ask you some questions on the physical aspects of what is rolling noise. And so let's start by the contact model that you chose. So you start from the assumption that Hertz's law is applicable to your case, and especially the pressure distribution is parabolic. So there is at least two effects that could impede this assumption. The first is dynamical effect, and the second is viscoelastic effects. So what could you say about dynamical effect? I mean, Hertz's theory is, of course, a static solution of the elastodynamic equation. So in principle, you can't apply it directly to rolling noise. So what could you say on the range of application of Hertz's law to your case?
I would say that in the time domain model, we're representing it essentially as it's a series of static snapshots. And because of the fact that we're not taking into account the dynamic effects in the contact model, that is what we're trying to do in the dynamic model with our spring mass damper system. Though again, I did not directly investigate what the frequency limits was for that, but it is a good point, and that's also something that needs to be considered when you have things like the damping loss factor of your materials, which are frequency dependent. We have that frequency dependence in their response, but not in the contact model.
Okay, but the classical argument for the application of Hertz's law is to compare the wavelength of the vibration in the wheel with the contact size. So in your case, it would be very easy to do it. The contact size, as you say, is about a millimeter, if I well remember, and maybe the wavelength is much more than that. That's all. So for the second effect, viscoelasticity, what we know about viscoelasticity is that Hertz's law, the distribution of the normal pressure is no longer symmetrical, but it is higher in front and lower in rear. So did you observe such an effect in your measurements?
When you say in the front and the rear, do you mean towards the direction of rolling and away from the direction of rolling?
Yes.
When I tried to directly measure the pressure contact between the wheel and the floor, no, that might just be because the paper is not sensitive enough. But also, when looking at individual snapshots in time in the model of the contact area, I don't recall seeing a noticeable difference in the position, either front and back, in that contact stress profile.
Okay, so I know that it's very difficult to measure, but at least you could have performed a numerical simulation in order to test the effect of viscoelasticity and just to observe if it is a main phenomenon or if this is just negligible. So it's very classical in words. Viscoelasticity, it's well known that in the tie rod contact and stance, the normal load is higher in front. than in rear. And also just another aspect of the distribution of pressure of stress in the contact. You did not say anything about the transverse stress. So what could we say?
I made the assumption that it was negligible because I have in train wheels, because of the both curvature of the wheel and the curvature of the rail, that's something which is often taken into account. But in my scenario, I am ignoring transverse stresses. Is that a correct assumption? Technically, I can't say for sure because I didn't measure it or go further into it.
It is negligible for the phenomenon that you observe, that is the sound radiation. But for instance, if you were studying the rolling force or the tribology more generally, it will of course not be negligible. That would be.
If my focus was on the force, really, then yes, it would be, including that would be would yield a more accurate contact force result.
No, well, I mean, it is negligible because you are interested only in the sound radiation. So that we know that in sound radiation, only the normal vibration is of importance, but not for the rolling resistance. Okay. Well, that's just a comment. These comments could be added in your manuscript very easily in order to clarify. But anyway, I would like to move to chapter 3. So you introduced, especially, would you like to move to slide 23, please, of your presentation? Yes. So you introduce the normalized stiffness as the ratio of the actual stiffness with the product of width and Young's modulus. Yes. But my remark is that it would be a better idea to normalize not with the product, but with the infinite cylinder. Because for the infinite cylinder, we know that the stiffness is constant, or we know that the deformation of the wheel is simply proportional to the load, and that the proportionality factor is pi over 4 times W and E. So the only difference for you is to introduce factor pi over 4 over in the definition of your normalized factor. So that's just a remark. Okay. But this remark may be important. So in your manuscript, if I observe page 94, you presented two figures in which we can see the stiffness versus Young's modulus and stiffness versus width of the wheel. Okay, and so that figures are very interesting because if I compare with the infinite cylinder, you gave the relationships of the infinite cylinder. They are given in your manuscript in page 53, and these are equation 2.20. Okay, and so what we can see is in the case of the infinite cylinder, the stiffness is simply proportional to Young's modulus. And we also see that the stiffness is proportional to the width. This is exactly what you observed in this figure. So it's nice, but it means that your wheel is close to an infinite wheel, one infinite cylinder. Yeah. Also, I did not success to reproduce the value of the vertical axis with infinite cylinders. So maybe I did an error, but I obtain a difference by factor 10. So if I assess this contact stiffness of the infinite cylinder with that that you obtain in these figures, so I don't know if this is my error or if there is a problem in your figures. What else? Anyway, I think that what you did in to define the normalized abacus is a very good idea. Very good idea, because from that we can directly observe if the wheel is close to the infinite cylinder model or if it is far from that. So that's a good point. Now I have also some other questions on the dependence of the running noise with the running speed. So if we observe the frequency spectrum of your running noise, we can see that the spectrum is more or less flat, but with a cutoff frequency about 2 kilohertz. I don't remember exactly what it is on your presentation. So do you think that this cutoff frequency may depend on the running speed or no?
So interestingly enough, it does.
Yes.
But in observations, the overall shift at all frequencies upward when you increase the speed was quite a bit larger than the forward shift you would see in frequency from the changing speed. But it is there, and it's expected to be there, because when you change the frequency, you change the wavelengths of the roughness moving through the contact area.
Yes, except if the rolling noise is due to impact of roughness, in which case an impact is more or less the same or has the same spectrum independently of the rolling speed.
For an individual impact, yes.
Yeah.
Now, if you have a series of impacts, then the impact frequency due to each time the wheel goes around the flat spot, that will change.
Yes,
so
yes, you're right. You're right. Also, that we know is usually we observe that the sound pressure level is a power law of the rolling speed or sliding speed. Do you have an idea of the value of the exponent of in your case?
No, that's not something that I calculated. Again, I was focusing on seeing visually on the graphs if there was a similar relative change when you change the speed, but I did not directly calculate what the relationship was. No.
Yes, that's a pity, because to have an idea of this exponent could give you the answer about the relative contribution of the different physical phenomenon responsible of the rolling noise. I mean, when rolling a cylinder on rough surfaces, you have roughness noise. I mean, the impact of roughness into the cylinder. You also have impacts, because as you explained, the wheel may be flat, and also you have sorry, the fluid. So Denis asked the question about fluid pumping, and we know that fluid pumping presents an exponent about 2, if I well remember, while the exponent for roughness noise is about 3 and 4, about 1 or less than 1. So to have an idea of the value of the exponent in case would allow to say if fluid pumping or roughness noise is dominant or no.
Okay.
What else? Yes, final questions about the effect of added load. So in your manuscript, you show that when you increase the load, you decrease the noise. Do you have an explanation for that?
The explanation that I would give is when you are increasing load, you're increasing the mass of the system. So you have a lower excitation because there's more inertia, more energy is required to excite that system. So that is why we end up seeing a lower vertical excitation. Even though the injected force is now higher, the effect of increasing the inertia overpowers the effect of increasing the injected force.
But maybe there is also another explanation for that, huh? Because when you increase the load, you crush the roughness, and so you should compare the crushing of the wheel into the surface with the roughness of the surface. And so maybe there is a transition between a roughness effect, which is very high for low load, and maybe roughness simply disappears when the load is too high.
It's true.
Okay, so that's all from me. So congratulations again. And now I would give the floor to Fabien Chevillotte. Fabien, please. Would you like to ask questions or comment? If you prefer?
Yes, thank you. I don't have a lot of questions. So first, I will do a general comment about Matt. So Matt, I want to thank you. Matt was our first full-time thesis at Matelis. And for us, it was a very good experience because I know from the discussion with a lot of professors that it's very difficult to find a good candidate. And for us, it was the case. I think we had a very good candidate with a very good flow during the thesis. The first year with a good handling of the topic and very good discussions. And then Matt has shown very good autonomy through the second and the third year. So it was very good experience for us. Matt has very good skills. He's an actual leader. He has very good skill for project management. He's very well organized. I think you have seen that he has a good communication and writing skills. He was a leader for one demonstrator because this thesis was in an ITN project, an European project with a lot of coordination. He has shown very good integration, social integration. He has learned French within 1 year. So it was all these good points I want to point it out. I have some general questions, just three general questions. The first one is, in your literature review, you say that you have three types of rolling model: time domain, frequency domain, and hybrid model. You consider that your model is a time domain, frequency domain, or hybrid one? This is my first question.
I would consider mine to be a hybrid model because we start in the time domain with our contact events, and then we move to the frequency domain to obtain the sound power radiated into the floor below.
Okay, so using this kind of hybrid model, do you think it could be used for impact model to use this description in the time domain and then to switch in the frequency domain to have a more accurate impact model, or not necessarily for a tapping machine, but for example, for the Japanese ball, where you drop a ball on the floor with just one impact?
It could. I can't say concretely. I haven't done a whole lot of research looking into the rubber ball, but I mean, theoretically, if you're interested in looking at the contact, such an event where you have particularly the deflection of that rubber ball, which can be time dependent on that impact, it might be beneficial. It might result in a higher estimation of the forces in play and a higher accuracy in the radiated sound power.
Okay. Then so I also have the question of if you have, after your 3 years of experience, if you have to redo this thesis, do you think to change the methodology? But you already answered to Wolfgang that you will start maybe with more experiments. I also have a question about the contact filter, the fact to use 1D contact model and the contact filter as introduced by Lundberg, for example. Can you recall why you think it's better to use your 2D or 3D contact model instead of using a 1D contact model with an additional filter?
The benefit of using 2D or 3D is simply it's less, I don't know if less work to be done is the correct way to say it, but if you have a 1D model, you have to develop analytically your own filter. So you have to pre-filter your roughness and make sure you're doing it correctly. So it's another thing to go wrong. Whereas if you have a 2 or 3D model, the model will naturally give you the context filter, so you don't have to worry about whether or not your analytical filter is correct or not.
Okay, thanks. And my last question is about the methodology you employ in the chapter 3 for estimating the stiffness of the wheel. We have a lot of discussion about the possible link between the elastic parameter of the floor and the parameter we have to use for the contact model. You said during the presentation and in the manuscript that in the contact model we are focusing on the, I would say, the elastic parameter at the surface, so close to the contact. But you can have in the multi-layer spring mass system. And my question is, if you consider the first layer of the floor, could you use a similar methodology to estimate a link between the hardness parameter and the elastic parameter of one homogeneous layer?
That is a conversation we've had multiple times. It is an interesting question, particularly because oftentimes for flooring materials and wheel materials, what's published by the manufacturer is not the elastic parameter, it is the hardness parameter. And I did a little bit of research into looking into that at the beginning, but based on the dialogue that I had seen taking place between researchers in the material science field, it's a very difficult question to answer, and there are people that are still actively trying to answer it. Can you link the hardness to the elasticity? Because you can change the hardness of a material without changing the elasticity of it. If you add a different surface stiffness, or if you use any type of heat treating on a metal, for example. So if you were going to try and find a link between elasticity and hardness, it would need to be able to either ignore this or account for this. And I'm not quite sure, based on my understanding of material science, if that can be done.
Okay, so it was my last questions, and thanks once again for your presentation and for these 3 years. Thank you, Matt.
You.
So thank you, Fabien. Now let's move to the second supervisor. So Nicolas, Totaro, if you have comment, please, or questions.
I don't have any question, but I have some comments. Yes, first I want to thank you for your presentation. It is a really nice presentation, and I fully agree with Fabien. It was really a pleasure to work with you during these 3 years. And yeah, for example, the thesis, you wrote it in a really smooth way, and it was really a pleasure for me to read it and to slightly correct it. Again, you did a really good piece of work, and yeah, it was really a pleasure for me to work with you. Again, I fully agree with Fabien. You are really autonomous, and you are really efficient in the way you have to work. I did like your really professional way to conduct research. And also in a particular framework, you mentioned it, the ITN framework is quite particular because it asks you maybe more skills than in other classical PhD. because you need to organize things, you need to present your work to the committee and so on. So you have, I think you have done this really well, as I heard that. And also, last thing maybe I have to say is something that does not appear in your presentation, and that I was really impressed about is the way finally you, the fast way you, how fast you learn French. It was really impressive for me because I think French is not so easy to learn, and now you are, I think you speak really well French, and this also is really impressive. So that's all. I don't have any other question. I think you have you had a lot of question from the other members of the jury. So I just want to thank you again.
Thank you, Nicolas.
So thank you, Nicolas. Is there any further question from the jury? No?
No.
Okay, in that case, I will propose to close the question session. And so now we need to deliberate. And so I will ask to Matt Edwards to let us, please.
Yes. So I will now remove you guys from the live stream, so you can no longer be heard.
Yeah, that's kind of important. And I will leave the room. For those on the live stream, they're going to deliberate for an unknown amount of time. If you want to stick around and wait for the decision, you can. If you don't, you're welcome to leave. So I will leave now and let you guys deliberate. Is that okay? Yes. So currently, they are only seeing me. They cannot hear you right now. Yeah. Yeah. All right. So I will leave. Okay. Yes, I can. Mm-hmm. 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 Yes. Yes. Almost to the day. Mm-hmm. Mm-hmm. Thank you. Thank you. Thank you, everyone. Uh, I will add. Apparently, the audio isn't working on the live stream, but I will just let everyone on the live stream know that they passed me. So that's exciting. Thank you to everyone. This has been a wild and crazy journey. I tell everyone when people ask me about my decision to come here, I usually say that it's the craziest thing I've ever done. Move to a foreign country in which I do not speak the language and do a PhD, which was never on my list of things to do. But I firmly believe that it is what was the way that my life was headed, and it wouldn't have happened if it wasn't what I was supposed to do in life. So this has been an extremely fruitful last 3 years. I've learned more in the last 3 years than I've learned in many, many years of my life. And very, very thankful to everyone at Madeleine who has been incredibly supportive of all that I've done. Thankful to everyone at INSA and at Accutect for all of the support. And of course, thank you to all of these jury members for taking time out of your day to not only be here and watch my presentation, but also read my extremely long manuscript. So I appreciate that greatly. Good question. So I have been offered and have accepted a position to stick around at Madeleine afterward, which is exciting. So my plan will be to stay here in Lyon for the foreseeable future and work on implementation of this rolling model into our piece of software that we have, as well as managing a different project called Silent Prop, which is going to be on silent propellers for electric airplanes. Yes, very exciting. Completely different than what I've done for the past 3 years, but exciting nonetheless. Yes. No? I think we can, yes. Yes, indeed. Thank you. Bye.